Imagine you and I buy two perfect clocks, same brand, same model, same battery. We start them together. They agree exactly. Then you take your clock on a fast trip. You come back. Now the clocks disagree, not by a little. By a real amount you can measure. That sounds like a magic trick. It is not. It is physics. Richard Feynman had a clean way to handle questions like this. He did not start with poetry. He started with a method. He said, do not begin by asking, what is time? Begin by asking, how do we measure time? Because in science, a word means what you can measure. So let us do it his way. Let us build time from the ground up. In plain English. First question, how do you measure time at all? You pick something that repeats. A heartbeat, a swinging pendulum, a dripping faucet, a turning wheel. Each repeat is a tick. Count the ticks. That is your time, but you notice a problem fast. Some repeats are not steady. Your heartbeat changes. A dripping faucet changes. A mechanical clock drifts. Even the Earth is not a perfect clock. Its rotation is not perfectly constant. So what do? You compare clocks. You do not trust one clock blindly. You test one clock against another. If two different kinds of clocks agree day after day, you trust them more. If they disagree, you learn something. Either one clock is unreliable, or your idea of time needs to be refined. This is Feynman's key move. Time is not a mysterious substance. Time is a measurement system. It is built from regular cycles, and it is confirmed by agreement. So in physics, a practical definition of time looks like this. Time is what a good clock measures. A good clock is one that agrees with other good clocks. That sounds circular. It is, and that is the point. Science often works like that. You define a quantity by a procedure. Then you test the procedure by consistency. Now let us push one layer deeper. Why do we even care about time? Because time lets us describe change. If nothing ever changed, time would be meaningless. But things do change. So we use time to describe motion. How fast? How slow? How long? So the moment you talk about motion, you connect time to distance. Speed is distance divided by time. If you know distance and time, you get speed. If you know speed and distance, you get time. So time and distance become partners. Now here is a subtle trap. How do you measure distance well? Often you use light. You send out a pulse of light. It reflects off an object. It comes back. You time the round trip. Then you convert that time into distance. So distance can depend on time, and time can depend on distance. This is why Feynman warns you, do not expect a perfect dictionary definition. Expect a measurement framework. Now we reach the big question. Do all observers share the same time? Most people assume yes. They assume there is one universal now, one universal present moment, one universal clock behind everything. Relativity says that picture is wrong. Not because reality is weird for fun, because measurement forces it. To see why, we need one concept. We need simultaneity. Simultaneity means at the same time. That sounds obvious, but it hides a problem. How do you decide if two distant events happened at the same time? You cannot be at both places. So you need clocks at both places. And those clocks must be synchronized. So you need a method to synchronize distant clocks. How do you synchronize distant clocks? You send signals, usually. You send light signals. You can do it like this. You send a light pulse from clock A to clock B. Clock B reflects it back. Clock A measures the round trip time. Then you set clock B so that the one-way time is half of the round trip time. That is a reasonable rule. It is also the standard rule in special relativity. Now add one crucial fact. Light has a fixed speed. It does not change with the motion of the source. It does not change with the motion of the observer. That is the core of special relativity. Once you accept that, A famous example is satellite navigation. Think about what a navigation satellite must do. It must tell you where you are, but it cannot point at you with a finger. It has to do it with timing. A satellite sends a signal, your receiver hears it. The receiver measures how long the signal took to arrive. Then it turns that time into a distance. Do that with several satellites, and you can solve for your position. So the whole system is a timing machine. That means the clocks have to be extremely good, and it means relativity is not optional. Satellites move fast compared to you on the ground. So by special relativity, their clocks tick differently. Satellites are also higher in Earth's gravity field. So by general relativity, their clocks tick differently again. The two effects pull in opposite directions. But the net difference is still real. If you ignore those corrections, the position solution drifts. It drifts fast enough that the system becomes unreliable. So when you use your phone to get directions, you are using Feynman's lesson. Do not argue about time. Build clocks. Compare clocks. Correct clocks. Now let us slow down and make that clearer. There are really two different issues here. One is motion. Motion affects time comparisons. That is special relativity. The other is gravity. Gravity affects time comparisons too. That is general relativity. Feynman's style is to keep the core idea. A clock is a physical process. If the physics of that process is affected by motion or gravity, then the clock rate shifts. Not because the clock is weak, because time is not the same everywhere. In plain English, gravity changes how time flows. Clocks deeper in gravity run slower than clocks higher up. Again, this is not a feeling, it is a comparison. You only see it when you bring clocks together or link them by signals. So now we have 3 layers of time. First layer. Time is measurement. It is the counting of regular cycles. Second layer. Time depends on motion. That is time dilation. Third layer. Time depends on gravity. That is gravitational time dilation. Now, at this point, you might ask a very fair question. If time depends on motion and gravity, then what is a second? Is a second still a second? Yes, but you have to be precise about what you mean. In physics, you define a second by a standard procedure. Today, the second is defined using an atomic transition. It uses the cesium-133 atom. The definition says that 1 second is the duration of 9,192,631,770 periods of radiation linked to a specific transition of that atom. So the second is tied to an atomic rhythm. It is not tied to the Earth. It is not tied to the Sunday. It is tied to a stable physical process. And that is very Feynman. You do not define time by a story. You define it by a repeatable experiment. Now here is the important part. Even with that definition, you can still have different elapsed seconds along different paths, because the second is the unit. But the amount of proper time accumulated depends on the path through space-time. So a second is a standard tick. But how many ticks you collect between two events can differ for different observers. That is why the two clocks at the start of this video can disagree. Now let us bring back the phrase that helps organize everything. Proper time. Proper time is the time measured by a clock along its own journey. If you stay with your clock, that is your proper time. If someone else watches your clock move, they assign a different coordinate time to your motion. Both descriptions can be consistent. But your clock always measures your proper time. That is what the clock does. So when you feel time passing, you are feeling proper time. You are not feeling the universe's coordinate grid. You are feeling your own physical processes, your metabolism, your neurons, your heart, your cellular chemistry. All of it is a set of clocks. Now let us talk about a confusion that never dies. People hear time dilation and they think it means everything is an illusion. They think reality becomes subjective. That is not what physics says. Physics says measurements depend on the frame, but the laws stay consistent and causality stays intact. Cause still comes before effect for events that can influence each other. No one can send a signal faster than light. That limit protects the logical order of cause and effect. So relativity changes your picture of now, but it does not turn the universe into nonsense. It turns it into geometry. It turns it into space-time. And space-time is not a vibe. It is a structure with rules. Now let us do a simple reset. If you had to explain the first half of this story in one sentence, it would be this. Time is what good clocks measure, and good clocks do not always agree when you compare them across motion and gravity. That is already enough to change how you see the world. But we still have the second half, the part that affects your life every day, the arrow of time. Because even if you accept relativity, you still wake up facing one direction. You still move from childhood to old age. You still remember yesterday and not tomorrow. So let us ask the other big question. Why does time feel like it has a direction? Feynman's clearest answer is not mystical. It is statistical. It is about entropy. Let us keep this simple. Imagine a deck of cards. A perfectly ordered deck is special. There are very few ways to get that exact order. A shuffled deck is typical. There are countless ways to get a shuffled deck. So if you start with order and you do random shuffles, you tend to move toward disorder. Not because disorder is a force, but because disorder is common. Order is rare. That is the core idea. Now swap the deck for something physical. Imagine a tank of water. On the left side, the water is dark blue dye. On the right side, the water is clear. There is a divider in the middle. You remove the divider. What happens? The dye spreads. The blue mixes into the clear. Soon you get a uniform color. You never come back later and see the dye gathered neatly back to the left side. Why not? At the microscopic level, water molecules bounce around all the time. They collide. They scatter. The basic laws that govern these collisions do not forbid reversal. In principle, you could reverse every molecule's velocity. In principle, you could run the system backward, but here is the issue. There are unbelievably many microscopic arrangements that look mixed. There are unbelievably few microscopic arrangements that look perfectly separated. So when the system evolves, it almost always moves from special to typical. From separated to mixed, that is the arrow of time, you see. It is not a separate law that time must go forward. It is the fact that the future tends to contain more typical states, more mixed states, more probable states, and this is what entropy is tracking. Entropy is a measure of how many microscopic arrangements match the same big picture. High entropy means many possible microstates match what you see. Low entropy means few microstates match what you see. So low entropy looks special. High entropy looks ordinary. When systems evolve, they tend to move toward high entropy because there are more ways to be there. Now connect that to your life. Why do you remember the past? Because the past left records. A footprint is a record. A photograph is a record. A fossil is a record. A file on a drive is a record. A memory in your brain is a record. Records are physical. They are not magic. They require energy. They require changes in matter. They require heat to be dumped somewhere. And in practice, record making increases entropy overall. So memory and entropy are linked. You remember the past because the physical world created traces. Those traces are easier to create in one direction than the other. So the direction you call past is the direction where the traces point. Now, ask a sharper question. Why does the universe have an entropy arrow at all? Why is there a direction? Why did it not start in a typical mixed condition already? This is where Feynman says something that sounds simple, but is deep. The universe must have started in a very special state, a low entropy state. That special beginning sets the direction. From that beginning, typical evolution moves toward higher entropy. So the arrow of time is not only in the laws, it is in the starting condition. It is in the history of the universe. That is why the future looks different from the past. Not because the equations demand it in a simple way, but because the universe started out special. Now let us pause, because this can feel like two separate stories. One story is relativity, It says time depends on motion and gravity. It says now is not universal. It says clocks do not always agree. The other story is thermodynamics. It says the future is the direction of increasing entropy. It says mixing happens. It says unmixing is absurdly unlikely. So which one is time? Feynman would say, both are telling you something real. Relativity tells you how time compares across observers. Thermodynamics tells you why time feels directional in daily life. One is about measurement across frames. One is about probability in large systems. They are different lenses on the same world. Now let us bring everything back to the hook. Two perfect clocks. You start them together. They agree. One goes on a fast trip and comes back. They disagree. That disagreement is not opinion. It is a measurement. It is what happens when two clocks take different paths through space-time. Now add a second detail. Even if you leave motion aside, time can differ with gravity. A clock higher up can tick differently from a clock lower down. Again, not a feeling, a comparison. Now add the third detail. Even if you accept both of those, the reason you experience time as moving forward is tied to entropy. It is tied to mixing. It is tied to the fact that the universe began in a special low entropy state. So what is the cleanest plain English picture you can keep? Here it is. Do not picture time as one invisible river. Picture a web of clocks. Each clock is a physical process. Each clock measures its own proper time. When clocks move differently or sit in different gravity, they accumulate different time. When clocks meet and compare, differences can appear. And the reason your life has a direction is not because time has a built-in motor. It is because the universe has an entropy gradient. It started in a special state, and it is moving toward more typical states. That creates an arrow. That arrow is why eggs break, why smoke spreads, why memories point backward. Now, let me give you a final thought experiment to lock it in. Imagine you have a perfect clock in your pocket. It can be a light clock or an atomic clock. It ticks with perfect regularity. Now imagine you live your whole life without ever comparing it to another clock. In that private world, time is simple. Tick after tick after tick. Now imagine you step out and meet another observer. They have their own perfect clock. You compare. Now the universe gets interesting. Because comparison reveals relativity. Comparison reveals gravity effects. Comparison reveals the structure of space-time. This is why Feynman's method is so powerful. He keeps dragging you back to measurement. Stop arguing about the word. Decide on a clock. Decide on a procedure. Compare results. Then accept what nature says, even if it insults your intuition. Now let us end in a practical way. If this explanation helped you see time more clearly, subscribe to the channel. That tells the platform you want more physics in plain English. And leave a comment with one question you want answered next. Ask about the twin effect. Ask about simultaneity. Ask about entropy. Ask about time and gravity. I read the comments, and I will use your questions to build the next video.